Welcome to Differential Equations. This video will provide instruction to what differential equations are, some examples of what they might look like, and what the goals are in this first course on differential equations. So, this class is called Differential Equations, so what are they? What are these things, and why do we care so much about studying them? Let's think back first to Calculus 1. In that class, we set up and defined this idea of a derivative. And what was that? Well, the derivative of a function is an expression that tells us the rate of change of that function. In Calculus 1, we use this idea to talk about optimization, being able to figure out where a function is maximized, like where the rate of change was 0. Things like related rates, being able to relate one rate of change to another to solve physical problems, things like that. I want to extend beyond that a little bit for this course. So if I have a differential equation, really that's going to be an equation that involves the derivative of some function. So what this thing is it's really a way that we can describe or explain what the rate of change of some function is. And when we think about solving these equations, that means that I want to use this description of the rate of change, sort of go backwards and then figure out what is the actual quantity or thing doing, because I know what the rate of change is. So taking the rate of change and solving to then figure out what the actual function is itself to see how that thing behaves, where it reaches certain values, does it get bigger and bigger or smaller and smaller? How is this going to behave based on knowing how the rate of change works? This idea is very, very common and very important in science and engineering fields because a lot of those fields are built around having a way to describe a rate of change and needing to take that information and use it to figure out what's going to happen to my actual system over time once I know about that rate of change. So let's see some quick examples of what these might look like. Even though we don't know how to solve them, don't know how to handle them yet, we'll just look at what these equations might be and how they might come about in the science and engineering fields. So here's one example. It is a mass balance for a chemical in a well-mixed reactor. As of now, we can assume this equation works the way it does. In engineering classes, you would look at why this equation is this way and how do we know that this physical system, this well-mixed reactor, gives rise to that equation, but that's not the point for this class here. What we see here is we now have an equation for here an unknown function c of t. The goal here will be to find c of t from this information. Now we have in this equation here, we have a derivative. Right, here is the derivative of this function c, and I have written that derivative in terms of some constant values like this here, and the unknown function c itself. That's going to be a standard form for these differential equations. I have the derivative that I've written in terms of some constants, the function itself, and or the independent variable t in this case, which doesn't show up here, but it could. As another example, we can talk about fluid flow through a pipe. This is a pretty standard type of equations you might see. It builds to, in more complicated cases, the Navier-Stokes equations, but this is a very simple version of them. The unknown function here is this u of r, which is the velocity at a given radius. And we have an equation here involving derivatives of this function. Right here I have the first derivative, and here I take a second derivative of that product. And that being equal to this alpha gives me an equation that I could then use to figure out what the fluid flow looks like. As we build into this more, you'll see things more often, but we also have things called boundary conditions, which are telling us certain values of the function that's going to help us actually solve the equation eventually, once we get to that point. And as one last example, we have a system here of differential equations. And a system means I now have two unknown functions, x1 and x2, both of which are changing, and the way they change interact with each other. They intermingle in how they are developing. Right, so x1 here depends on x1, but the change of x2 also depends on x1, and it turns out this mu coefficient here depends on x2 as well. So x2 is also here, here, and hidden up in here. So these two things don't develop on their own, they develop together, and that gives rise to a system of differential equations, which is more complicated to solve, but we'll have techniques we'll develop to handle these over the course of this semester as well. What are the goals for this course? The main goals over the course of this course in differential equations include the following. So first, we want to learn how to write differential equations to model physical systems. Not as complicated as the previous ones that I just discussed, but more simpler ones that are easier to visualize what's going on. 2, we want to learn how to analyze and solve these equations, and then interpret those results in the context of physical systems. For instance, if I solve that reactor mass balance problem, I then want to say, okay, if I know what the profile is over time, what can I say about the concentration of stuff in the reactor over time? Or if I want a certain amount of product, when should I stop the reactor? Those are the questions I'll be able to answer once we can solve the differential equation. And en route to these things, we'll also want to learn a couple other sort of side topics on the way there. We want to learn the basis of linear algebra in order to analyze systems of differential equations. DEs here mean differential equations. And we also want to learn about numerical models and methods for approximating solutions when we can't solve them out by hand. And that's really where we're headed with this course. We want to learn what differential equations are, how we can approach trying to solve them, and how to use numerical models when we can't solve them by hand to get similar sorts of results and conclusions out of them from numerical solutions.